Okay, any questions before we start?
How come the evaluation wasn't done last semester?
It was. Probably you were absent. Other questions? You missed your opportunity.
Me and like these other guys as well. Coincidence.
If you remember, the last thing we were discussing last week was RL circuits where we had an inductor and a battery connected through a resistor. So this was the RL circuits. And we had seen that the current as a function of time doesn't really increase instantaneously. It just takes a finite amount of time to increase to its eventual value, which was, if we call it I0, I0 was just epsilon over R. So the inductor being just a wire, a coiled wire, doesn't really affect the current when it becomes this constant value, but what it does is it just causes the current to increase gradually because the inductor basically resists any change tries to resist, let's say, any change in the current. So it cannot just raise instantaneously, it can only raise slowly so that the change in the current is small. Any questions on inductance, inductors, RL circuits? Okay, so what other kind of circuit we can study? RC, that's the simplest one. Now the RC circuit, we have a capacitor which is initially charged, and then we have an inductor. So we had already studied how we can discharge a capacitor through a resistor. It's LC. Yes, this is an LC circuit. Now, before we had studied how to discharge a capacitor through a resistor. Now it's as if we are trying to discharge a capacitor through an inductor. There's no resistance in this circuit. Nevertheless, the current cannot go to infinity because you see, we always say that the current is the potential divided by the resistance. If the resistance is infinite, it seems that the current should go to infinity. But remember, the inductor always resists the changes in the current. So if initially the current is 0, it cannot just go to infinity. It only can increase gradually. So let's see what will happen in this circuit. So initially, let's say this is the positive plate, this is the negative plate. The charge in the capacitor at t equal to 0, this is equal to 0. Let's say the current at t equal to 0, this is equal to 0. So at t equal to 0, we are just closing a switch, closing the circuit. Now what will happen? Well, the capacitor will try to discharge itself. So let's see, this is the Q as a function of time. This is I as a function of time. So initially we have, initially we don't have 0 charge. Initially we have the Q0 charge. The current starts from Q0. No, the charge starts from Q0. The current starts from 0. Then, as your friend pointed out, the charges will start flowing through from the positive to the negative terminal, negative plate. But remember, the current cannot just increase instantaneously. It has to increase slowly. So the current will start dropping the charge. And remember, the current is nothing but the derivative of the charge. So initially, since the current is 0, the charge as a function of time, it should start flat. But then the current gradually increases. Now the current will increase. So as the current is increasing, the charge will start to decrease faster. And then after some time, we will reach such a point where now there is no charge. There is no charge in the capacitor. There is a current running in the circuit. Now what? So we said that initially it was the capacitor that was driving the current. So that is why we said that there is an increase in the, there is a decrease in the charge, increase in the current, gradual increase due to the inductor. But now the charge is 0. So what will be driving the current now, if anything? So now remember there is the inductor. And what?
Before we go on,
Yes.
the time derivative Q integral is minus. So current has been. Okay. So another thing. These graphs are not consistent because the decreasing rate of Q is increasing in time.
Thank you. Okay, now, there is 0 charge in the capacitor. The capacitor is no longer driving a current. So what will happen to the current? Will it just go to 0? Remember, there is the inductor. You see, what does the inductor do? Inductor resists any change in the current. So it tries to keep the current constant. So now at this point, there is no charge, so it's not the capacitor that is driving the current, but the inductor will keep driving the current in the same direction. It doesn't want the current to go from some finite value to 0. So it will just keep the current running. But when the capacitor is empty, if the current keeps running, this plate will become positively charged. Because the charges started to move. When the charge is 0 in both of the plates, the current still keeps going. So basically, the lower plate will be positively charged this time. So the charge in the capacitor, which we defined as the charge of the upper plate, now becomes negative. Yes?
Does it oscillate in time?
That is what we are arriving, basically. So the current will start running. We'll keep running. But this time, there's no the capacitor is kind of resisting because the charge in the capacitor now became negative. It's trying to run the current in the opposite direction now. But since the capacitor is trying to run the current in the opposite direction, but the inductor still wants to keep it in the same direction, but gradually the current will stop, slow down. But this time, the charge is now at some value. Now the current is 0. The inductor wants to keep it at 0. But the capacitor wants to run it in the opposite direction. So as the current starts to run in the opposite direction, that is the negative current, then the charge in the capacitor will also approach 0. So this is how it will change. Well, this is basically what we expect the current should be.
So if it was, let's assume it was a superconductor.
No resistance.
It's supposed to keep going forever.
Exactly. Now, if you want to see an example of that, search for the term superconducting cavities. These are basically RL circuits made up of superconductors, and they are used in accelerators. Now, if time remains, we will see what we will be shortly discussing what cavities are.
Well, in reality, it does not go forever, right?
Now, in reality, we don't have pure LC circuits except on superconducting ones. I mean, that is a real case, superconducting cavities.
Superconducting cavities, they can sway forever.
In reality, of course, all the wiring, if you don't use superconductors, have some resistance, and they will not go oscillate indefinitely like this. But what they will do is they will eventually lose energy due to the resistance, and the current will go to 0, the charge will go to 0 eventually. You see what's happening over here. The capacitor stores energy, and the energy stored in the capacitor is proportional to Q charge, it's charge squared. The inductor stores energy, and the energy stored in the inductor is proportional to the current squared. So initially, you have energy stored in the capacitor, no energy stored in the inductor. At this time, there is no energy in the capacitor, all the energy is now in the inductor. Again, at this time, all the energy is back to the capacitor where there is no energy in the inductor. So basically, the energy, the electromagnetic energy, let's say, is just goes back and forth between the capacitor and the inductor.
What would be the period of this motion? Let's assume those participants are average or we observe in our daily lives. What is the average time?
Well, let's see. This is qualitatively what we expect. Now let's do the quantitative study of this circuit. So this is our circuit. Now if I is equal to dq by minus dq by dt, this is our I. This is the positive direction of the current. So that's basically, if I is positive, that means the charge is decreasing, so this should be the positive direction of the current that we had defined. Now, how can we write an equation relating the charge, the current, and to each other, and so that we can solve for their time dependence? We don't know yet. We have to first, we know the Kirchhoff's rules. That is what will allow us to study this circuit. So let's start from here. From this corner. As we go to this corner, what is the potential drop? Well, the potential is increasing if Q is positive, so it's a minus Q over C. This is the potential drop as we go from point A to point B. Well, there is no potential drop as we go from point B to point C. Now, what is the potential drop from C to D? Well, it will be L di by dt. But is it positive or negative?
Di by dt is bigger than 0.
Well, in general, I mean, you see, in this circuit, what we expect, in certain regions, the I by dt is positive. In certain other regions, the I by dt is negative, so it will be changing in time. But that is not important in this equation. You can just assume, let's just assume that we are at a time in which the I by dt is positive. But if the I by dt is positive, it basically means that the inductor is trying to push the current in the opposite direction, because it will try to resist the change. If the current is increasing, it will try to lower it by pushing it in the opposite direction. But that is as if a battery with negative terminal over here, positive terminal over here. No, the positive terminal here, a negative terminal over here. That would push the current in the opposite direction. Right? If the I by dt is positive, so inductor will be trying to push it in this direction. So that is similar to a battery which has the positive terminal here, negative terminal over here. So the potential drop as you go from C to D is positive. It should be a positive number. L di by dt is positive. L di by dt is a positive. This is already a positive number, so the sign there is plus. Now we can make the other assumption. Assume di by dt is negative. Because as your friend pointed out, your friend had asked, what is the sign? And my claim is that the sign doesn't matter. Whatever the sign is, the sign of di by dt is, this sign over here it will be positive. Let's look at the other case. Di by dt is less than 0. The current is getting smaller and smaller. In that case, the inductor will try to push the current in the forward direction, in the positive direction. But that will be as if a battery which has the positive terminal over here, the negative terminal over there. But if that is the case, as you go from point C to D, the potential drop has to be a negative number. But L di by dt is already a negative number. So this has to be positive. That sign over there has to be plus so that this product is negative. Yes? Well, I mean, I don't know. I don't really see the reasoning. But for this simple circuit, it might be making sense. But for a more complicated circuit, how will you use that? I mean, you should avoid trying to relate this, what happens over here, to what happens over here. You should treat this one independent in this equation. This term should be independent of this one, or whatever the remaining circuit is. So you should be able to determine the sign of each individual term considering only that term without referring to the other elements. Now, we already know what the current is. We can relate the current to the charge. Don't forget this minus sign. Now, if you use that, then the charge set should satisfy this equation, minus Q over C minus L d squared Q by dt squared should be equal to 0. The current is this one. We should take the time derivative of the current. Well, the time derivative of the current is the second time derivative of the charge of the capacitor with a minus sign. That is why the sign over here is now minus, and here we have the second derivative of the charge. Well, let's look at this sketch. This is how we define the positive charge and the positive current. This is our definition. You could have defined it in other ways. Let's see, if the charge is decreasing, the current is positive. So if dq by dt is negative, I should be positive. So that is why we have that minus sign over there. Okay, good point. We always define I to be dq by dt. What is dq? Let's look at the meaning of these symbols. What is dq? So dq, in this definition, let's look at this part only. To define the current, you just pick a point on the wire. Since we are assuming the wire is infinitely thin, its cross-section is just a point. You pick up a point, let's say this point over here, and you count the charges passing this point in the positive direction. And that is dq. You divide it by the time it takes for all of this charge to move through this point. But let's see, the charge in the capacitor, though. Now, dq, on the other hand, is the change in the charge of the capacitor. So if some positive charge crosses this point, the charge in the capacitor is getting smaller. So the dq is a negative number. So this is why we have this minus sign over here. Again, you always go to the definitions, but not in the sense of the symbols, but you should also give meaning to these symbols. What do these symbols mean? What does this mean? And what does this Q mean? So that's the differences in the definition of dq over here and dq over there is why we have that minus sign. So this is our equation. Or let's write it in a different form. This is d squared q by dt squared. This is equal to minus 1 over LC times q. Now we have to find such a function q that when you take its derivative twice, it is itself multiplied by a negative coefficient. So which functions do you know? Let's go over the list. Come on, don't give the answer. You see, the solution of differential equations are quite often just going to the library, picking up a book of functions, going through those functions. That is a valid method. Now, for this simple equation, the solution is known. Let's just try this one. Q is equal to A sine omega t plus delta. Let's just give it a try. I don't know what omega is yet. I don't know what A is yet, or what delta is. But let's see if this equation will satisfy our equation. This function will satisfy our equation over here. dq by dt, this will be omega times A cosine omega t plus delta. And the second derivative will be minus omega squared A times sine omega t plus delta minus omega squared times q. This function, if you just take its derivative twice, it gives you the same function multiplied with a negative coefficient. So this is a function that we are looking for. This is a solution of this equation that we are looking for if omega squared is equal to 1 over LC. So q of t, the charge is a function of time. This is equal to A times sine 1 over square root of LC t plus delta. What is A, what is delta? Well, we have the two initial conditions. We know what the charge initially is. We have these conditions. Well, this basically tells us that A times sine delta, this should be equal to Q0. And remember, I is nothing but minus dq by dt. And when you evaluate the derivative of q, this is q, take the derivative, multiply by minus 1, set t is equal to 0. And that gives you A times cosine delta should be equal to 0. When you take the derivative, you also get the 1 over square root of LC, but that is not a constant, that is not 0, so we can just eliminate it. And if you just solve these two equations, you see, let's look at, well, since A is non-zero, we don't want A to be 0. If A is 0, our solution is 0, so you cannot satisfy this one. So cosine delta should be 0. If cosine delta is 0, sine delta is 1. So A is Q0. Now, if you also put in the delta, you would get Q of t is equal to minus Q0 cosine 1 over square root of LC times t. Now, plus Q0. And this is our solution. And how fast it oscillates, the oscillation frequency is given by this number over here. Where is? Delta. Well, we know the value of delta.
Delta is 5 over 2.
Yeah.
So we could write plus 5 over 2.
No, that's sine plus delta pi over 2. And sine, note that here I have the sine, here I have the cosine because of the delta. Okay. Which part? Okay. Is this point clear? I mean, you say this is probably the most important part in terms of the physics. Okay. Remember what the Kirchhoff's laws tells us. It tells us that if you start from a point, go around the loop, and sum all the potential drops or potential increases, the sum should be 0, because there is no potential difference between point A and point A. So we go from A to B. We go from the negative plate to the positive plate. Negative plate is always at the lower potential. Positive plate is always at the higher potential. This is negative, this is positive. So as you go from A to B, the potential drop is a negative number. And we know that the potential difference across a capacitor is Q over C. And the potential drop from A to B should be minus Q over C. This is the first term. Now the potential drop, or the EMF, across a capacitor, across an inductor, well, in fact, the EMF would be a more precise word for this. The correct word to use, the EMF drop as you go from A to B, or the total EMF, let's say. But I will stick with the term potential drop. Now, as you go from A to B, this is the potential drop. As you go from B to C, there is no potential drop because there is no inductor, there is no resistor, there is no capacitor. There is nothing that creates a potential difference between point B and C. From point C to point D, there is an inductor. Inductor creates a potential drop, which is given by LdI by dt, at least in terms of the magnitudes. The kind of the difficult part is to determine this sign. Is it a potential drop or a potential increase? Because it will also change whether the current is increasing or decreasing. Depending on whether the current is increasing or decreasing, this point will have a larger or a smaller potential than this point. Now, to determine this sign, you can just consider the possible cases, possible scenarios. One case is that di by dt is positive. If di by dt is positive, and remember, the inductor always tries to resist the change. If di by dt is positive, that is, the current is increasing in this direction, but the inductor will try to change that. That is, it will try to push the current in the opposite direction so that it will slow down the increase in the current. But if it is pushing in this direction, it is essentially behaving just like a battery, where this is the positive terminal, this is the negative terminal. But in that case, it just means that from C to D, there is a potential drop, a positive number. So we should add a positive number over here if di by dt is positive. So that tells me that this sign is positive over here. Of course, you can consider the other case. In the other case also, you will find that this sign is positive. Questions? Clear? Yes?
You said the other was a better word than potential line.
I think it was one of the midterm questions, right? You see, how do you define the potential? In which case can you define the potential? If you have a conservative electric field. So electric potential exists, let me put it in quotes, if E dot dl around the closed loop, this is 0. But E dot dl in general is equal to minus d phi b by dt. If there's a changing magnetic field, you cannot define a potential in the way we defined it, at least. Well, let's look at over here. Do we have a changing magnetic field? We have a changing magnetic field. So we cannot really define the potential the way we did it.
So why do we define the potential to exist in that specific case?
Well, this is the definition of a conservative electric field. And in electrostatics, electric field is conservative. Even in magnetostatics, the electric field is conservative, because this would be 0. Well, there are alternative ways of defining the potential, even if we have the magnetodynamics, but you will see it in 2 years. Now, any questions on how we obtain this equation for this simple circuit? And then, so here is the equation we have, just written in a different form. And then we have to just find a function that satisfies that equation. The next is just trial and error. Try this one. So we said that Q is A sine omega t plus delta. And if we take its second derivative, it is our function multiplied by a negative number. So this is our solution. Well, these then, of course, there is for whatever the value of A and delta are, we have these two unknown constants. Whatever A and delta are, this function does satisfy our equation. Now, we can determine those constants. And if you remember our mechanics course, your mechanics courses, there we had if you want to find the position of an object at a given time, you had to know the initial position and the initial velocity. Without that, you couldn't determine the final position. Just like that, if you want to determine the charge at a given time, t, you have to know the initial charge and the initial current in your circuit. And we already know that the initial charge is Q0, and initial current is 0. Well, initial current is nothing but the derivative of the charge as a function of time. So those two conditions tell us that A sine delta is Q0, A cosine delta is 0. Now, jumping from the sine to the cosine, I was kind of a bit cheating. You see, if cosine delta is equal to 0, we are happy with having sine delta is 1 or minus 1. So that you have to do some more work. Well, the easiest thing to do, we can just use the trigonometric identities. This is A sine 1 over square root of LCT cosine delta plus A cosine 1 over square root of LCT sine delta. Well, we know what A sine delta is. A sine delta is Q0. A cosine delta is 0, so this term is 0. A sine delta is Q0, so our solution is Q0 times cosine 1 over square root of LC times T. Now let's see what the current does. As a function of time, the current started from 0, and it's just oscillating between, let's say this is I0, this is minus I0, and I0, the maximum value, well, let's just write I of t we had already determined what the charge is as a function of time. I of t, this is equal to minus dq of t by dt. This is q0 over square root of LC times sine 1 over square root of LC times t. This is what I0 is.
So it's between 1 and 0?
It is oscillating between I0 and minus I0. The current will be constantly changing in time. And since there is no resistance in our circuit, it will always go from plus I0 to minus I0. It will never decay. And the time it takes to complete one full cycle, t is equal to 2 pi over 1 over square root of LC. Now, such a circuit that is constantly changing its sign is what we call an alternating current. Or simply AC. Now, any questions? No, this I0 over here is not the current at t equal to 0. That I0 is the maximum value of the current, this one. It is this height. Q0 is the maximum value of the charge, but it also coincides with the initial charge. Well, we will study circuits in which we have a battery, we have additional sources of AC. We will study that. Before we go for a break, let's also look at the energy stored in the capacitor and the inductor as a function of time. Now, the energy of the capacitor, this was equal to Q squared over 2C. This is equal to Q0 squared divided by 2C times cosine 1 over square root of LC times t, cosine squared. The potential energy in the inductor, the energy stored in the inductor, this was given by 1 over 2 Li squared. Here we have the I. This is equal to 1 over 2 L Q0 squared divided by LC times sine squared 1 over square root of LC times t. L's just cancel. So the UL is Q0 squared over 2C times sine squared 1 over square root of LC times t. And the total energy of my system is the energy stored in the capacitor plus the energy stored in the inductor. This is equal to Q0 squared divided by 2C. Well, this is nothing but the energy stored in the capacitor at time t equal to 0. Well, this is what we had already expected. The energy is basically transferred from the capacitor to the inductor back and forth, so that the total energy will always be conserved, and the total energy will always be equal to the energy stored in the capacitor at t equal to 0, because at t equal to 0 in the inductor there is no energy stored. Okay, now we can go for a 10-minute break.